there, my ATSEVS533 students. This is Dr. Shraki, and I'm welcoming you to Module 3 of our course, which is going to be about modeling the climate system. We're going to be specifically talking about numerical models in this module of the course. That's the kind of model you probably were thinking about when you signed up for this course. The kind of computer simulations that tell us things about the climate 100 years from now, depending on on what we do with regard to emissions of anthropogenic greenhouse gases and so on. These are what we're going to be talking about, how they work, what they do, and so on. Now, in the first part of today's lecture, what I want to do is I want to overview a few of the key points from that 100 level knowledge of climate modeling stuff that I gave you. And the reason why I want to do that is I know that not everybody goes through that stuff very well, and I know that not everybody reviews that material very well, and maybe has a hard time picking through what the most important points were. So let me just spend a little bit of time on that. Now, in that 100 level stuff, we talked about the fact that there are different kinds of models out there. This general idea of model is such a powerful idea in science and engineering. But models means lots of different things in lots of different disciplines. And what we're talking about here are numerical models. In the context of these climate models, what we mean is numerical models. They are climates that use the equations, they are models that are computer programs that use equations that describe the actual physics of the system that you're trying to simulate. And we had examples of that in that 100 level stuff that you saw. For example, there was this equation, I just stole this slide if you remember from NASA, where they were showing, they were modeling how a rocket was flying. Well, okay, one way to do that would be to make a physical model of the rocket and see how it flies. One way to do that would be launch a bunch of rockets and then use the statistics of how where they all landed to simulate it. But a numerical model would actually be applying the physics at every location along the way of the flight to simulate how it was flying. And this is in practice how climate models are actually done. You work with numerical models all the time, you just don't necessarily know it. Like, for example, at that 100 level presentation that you watched, we talked about the fact that video games are typically numerical models of the system. Like this racing game here runs numerical models of the car that actually knows the physics of the car. The car behaves in realistic, predictable ways because it's running in a simulation here that knows the physics of things like how much traction the tires have and how fast it can go around the turns and things like that. It's a numerical model simulating the behavior of a car. The game wouldn't be fun if it wasn't a realistic numerical model of the car. So a key slide from that 100 level presentation was this one that talked about how numerical models are computer programs that can simulate the real behavior of the system in question, whether that's a car on a racetrack or whether that is the climate system or any other numbers of, this is used all over the place in science. So if we're going to be running numerical models of the climate as climate scientists, we're going to need to know those equations that describe the physics of the atmosphere. Well, the good news is that's known perfectly well. We actually have amazingly good understanding, perfectly might be a strong word, we have a remarkably good understanding of the physics of the atmosphere. And it turned out, as we talked about in that 100 level lecture, it can be shown that there are 7 equations that describe the physics of the atmosphere in a prognostic or predictive kind of way. Those 7 equations are collectively known as the 7 primitive equations. I'm not really sure what the sense of the word primitive is in this context. Now, in that 100 level lecture, I actually went through each of them. Each of them is horrible. Mathematically, there's only one of them that's not a terrible mathematical mess, and that's the ideal gas law. But all of these are a set of equations that together, 7 equations and 7 unknowns, solves for how the atmosphere is changing due to its physics. Okay? How its motion is changing, how the amount of moisture in it is changing, how its pressure is changing, how the winds are changing, and so on. I don't mean on climate scales, I mean from second to second. And the model applies those 7 equations, solves those 7 equations at every little location on Earth where it has a so-called grid point, where it is going to compute, it's going to solve those 7 equations, which is not a simple thing to do, which will produce a forecast of the temperature, the winds, the pressure, the moisture, the cloud cover, all that kind of stuff, for a period of time in the future called one time step. And time steps are surprisingly small, on the order of a few seconds in general. It's actually quite a complicated bit of atmospheric science to figure out how they have to be a particular length of time in the future. But that's, oh my gosh, that's solving the CFL criterion. That's an enormous amount of math. Suffice it to say, it's not something we get to decide. Okay, it's the time step is just a short period of time in the future. You don't care about a forecast of the climate 2 seconds from now or 3.5 seconds from now or whatever. But then what you do is the computer model then takes that result of what is the atmosphere doing 3 seconds from now and solves it again, uses that as input for the 7 primitive equations and solves it again, and now you have 4 seconds into the future. And you use that as input again and you iterate forward, and now you have 6 seconds in the future, and you just do this farther and farther and farther, thousands and thousands of times. You solve these enormous equations, enormous systems of equations at every one of those grid points. And, a few thousand of these time steps in the future, you have a one-day forecast. And a few 100,000 of these, you might have a week forecast. And, a few billion of these time steps forward, and you might have a 100-year forecast or whatever. Because you have to apply all those equations, solve all those equations at every location on Earth, well, every place where you have a so-called grid point where you're computing the temperature, the winds, and so on. At every height in the atmosphere, again, they divide the atmosphere up into a whole bunch of these levels and layers, much like we did with our two-stream models, and where we did it in 2 layers. A typical number for state-of-the-art models these days is like 100. Okay? And you have to do it thousands and thousands of times. This, to get a forecast just for now, one way in which we are a bit in control as to how much computer power this is going to take is we do get to decide the resolution of the model. Now, for example, in the context of numerical weather prediction, which is the business of using these kinds of models to make forecasts of the weather tomorrow, the next day, etc., well, we might have the resolution of the model be pretty good. On this slide right here, I have an example of the grid that is used on a particular model. I have to admit, I can't remember which model's webpage I took this from. But it is, I don't know, you can see where the locations of the grid points are in that model, and, they're a few tens of kilometers apart or something like that. That's reasonably good resolution. State-of-the-art models might be a somewhat higher resolution than that. But, we get detailed forecasts of the temperature, the winds, the pressure, and so on at all these locations. We can see the difference between the weather at 2 locations that are pretty close together. That's a high-resolution forecast. But if the models are going to have high resolution, the problem is there's no computers big enough to run it at these very high resolutions for the whole world. If you have to have a grid point every few kilometers, every location on Earth, there's going to be tens of millions of these grid points. There's no computers with enough speed and so on to make these forecasts work. So they tend to be regional models. The kinds of forecasts that you see in your day-to-day, when you watch the Weather Channel, or God forbid, however else you get weather information, they typically come from models that run a regional forecast, where they maybe are only making forecasts for North America. And they make these high-resolution forecasts, but they're only for a limited domain. And that works for relatively short time scales on the order of a few days. But on the other hand, if there's some weather feature, say, over Asia, this model doesn't even know about it. It doesn't have any information about the pressures and temperatures over Asia. And if over the course of the next few days that storm system is coming to North America, this model can't make that forecast. It won't know about it because it doesn't know that storm system is out there. So this model has very high resolution, but the limited domain makes it only applicable for a few days in the future, which is fine for the art of numerical weather prediction, but maybe isn't such a great choice for climate modeling or even longer, even weather forecasting on the order of a few days or weeks into the future. We're going to need a global model. Global models have the grid points distributed all over the surface of the Earth, but they have to be, by definition, farther apart. There's just, maybe on the order of a few tens of kilometers to a few 100 kilometers apart. Otherwise, what computer could run this? I mean, there would be so much math as we increase the resolution, and every one of those grid points had to solve all those equations every time step. Well, we get a global forecast but a lower resolution. That's not great for finding out if it's going to rain this afternoon, or how the weather in Omaha will be different today from the weather in Fremont, which is, in case you don't know, the next town west of Omaha. It's maybe 20 miles away or something. A low-resolution model won't be able to tell you that. But if we just need to know about the climate, and we're going to simulate this out way in the future, a lower resolution model, but global, will be a good tool. So, just to give you a sense here, on this slide I said that numerical weather prediction, that's what NWP stands for. Numerical weather prediction models are typically regional, and they typically have a resolution 12 kilometers, maybe a little bit better as time goes by. There's research models that have resolution on the order of a few hundred meters, but you can't run those. There's no computer in the world that can run those fast enough that you could use the forecast for anything. If it takes your computer a week to make a forecast for 12 hours from now, well, what good is that, right? That's useful in a research context, but it wouldn't be useful like for flight operations or anything. The forecast is already gone before you can produce it. Global state-of-the-art models typically have a resolution of about 100, 110 kilometers, maybe a little better than that these days. I was recently at a conference where they were talking about 25 kilometer models. Oh my goodness, I mean, that's a lot of, changing from 100 kilometer resolution to 25 kilometer resolution increases the amount of grid points in the model by a factor of 16. Okay, so, as you improve the resolution, the problem gets out of control fast. You can see how, in general, this trade-off between resolution and the domain gives us a sense of how the computational needs of these high-resolution models spin out of control fast. The closer together the grid points get to each other, the number of grid points increases by the square of that. So, you have 4 times better resolution, you have 16 times more grid points. You need a bigger and bigger computer to run these things. The more grid points you have, the more calculations you have to do, and the more time steps and then the more times you have to do all those calculations as you get to some point in the future. It spirals out of control. So this is why we typically have, for like numerical weather prediction, there's these regional models, high resolution, so we can see regional, we can see the difference between the weather in Omaha and the weather of western Iowa and the weather of Lincoln and so on. We don't really care about that in a climate context. I don't really care how the climate of Omaha will be different from the climate of western Iowa 100 years from now. Okay, that's not a question I'm trying to answer. But as we talked about actually in that 100 level presentation, what kind of questions we are using for these models to answer is an important thing to understand. Typically they're going to be used to have some kind of experiment, where we will have like a control run of the experiment, where we'll run our climate model for 100 years out into the future, using, say, pre-industrial values of greenhouse gas concentrations. That'll be our control run of the model, and then we'll have an experimental run where we will have increased the amount of carbon dioxide in the model by a factor of 2, and we will run it for 100 years out in the future, which, oh my goodness, might take weeks even on a supercomputer to make that. And then we can compare. But what exactly are we comparing, and how do we know if this is working? I could see how I could write hypotheses about this, right? I'm a good scientist, I want to test a hypothesis. I could have a hypothesis that the experimental run has a higher global mean temperature than the control run, and I could test that. I guess I could write hypotheses about other things, like I could say that the temperature in Omaha is warmer than in the experimental run than it is in the control run. Or maybe I could even, but when? Wait a minute. Do I mean like as in 100 years from today the temperature in Omaha will be warmer than it is 100 if there's double carbon dioxide? Then I mean if the temperature 100 years from today would be if they don't double the carbon dioxide? I guess I could write a hypothesis like that, but I question what it would mean. We generally mean like as in we'll take the average global temperature for the last 10 years of the simulation in the 2x carbon dioxide concentration, the experimental run, and compare it to the global mean temperature in the last 10 years of the simulation in the control run. Okay, we're comparing apples to apples here. A long-term, average over 10 years, what was the global mean temperature when we doubled carbon dioxide by 100 years in the future? What was the global mean temperature if we didn't warm up the temperature, didn't increase the amount of carbon dioxide? We're comparing apples to apples there. And of course, skeptics come out of the woodwork when you say this stuff, and we beat this to death in that 100 level presentation, which, again, I'm expecting that you watched and so on. But, skeptics will clearly come out and say things like, well, how can scientists claim that to forecast the future climate 100 years in the future if we can't even always predict what the weather is going to be doing 3 days from now all that accurately? And, well, I mean, okay, to some extent I'm setting up a straw man argument here, right? I mean, I'm telling you this because I could take it apart. On the other hand, I'm sure you've had people tell you this kind, or you've seen people on TV have this kind of argument, that how does it, I mean, why should we believe any of these models and so on? And, in the 100 level thing, I kind of picked this apart in more detail and with more steps, but just to be clear here, weather and climate are two very different kinds of questions that we're trying to answer here. I mean, it's true that climate models and numerical weather prediction models, which are both numerical models, we're just basically running the climate model farther into the future than we are for numerical weather prediction applications. Well, they use pretty much the same equations, and they have pretty much the same sort of techniques, which it's true then, if the skeptic is doubting the numerical weather prediction, I can see why they want to doubt climate models. Both of these kinds of models, for example, start with so-called initial conditions, where we tell the model something about what the atmosphere is doing at a particular time. In the application of numerical weather prediction, we're telling them, like, at this hour, this is what the weather is doing. And then we integrate the model forward 12 hours, 24 hours, 36 hours to find out what the future will hold. In the climate models, it works very much the same way. We start with observations at some particular time, January 1st, 2000. And then we iterate 100 years forward into the future. And both of these models use the same equations of, the 7 primitive equations to produce their forecast for a one-time step in the future, and then just repeat that process. In the case of a numerical weather prediction model, it might be a few thousand times to get a 24-hour forecast, a 36-hour forecast. In the case of a climate model, it might be billions and billions of times to get out to a 100-year forecast. And so they are, I mean, let's not kid ourselves, they're very similar. On the other hand, and so I can see why a skeptic would say, hey, why should we trust these numerical weather prediction models when they often go bust only a few days? How can we apparently trust the same sort of model when it runs out 100 years into the future? Why should we trust those forecasts? It is not an entirely stupid argument. It does turn out, though, to be wrong. See, understanding why weather forecasts for, like, numerical weather prediction applications, why those forecasts sometimes go bust 24 hours into the future, 36 hours in the future, etc., are because of problems with these so-called initial conditions. This, again, was explained in more detail in those 100-level lectures, but just so we're reviewing the key points here. Initial conditions are how the model starts. What does it know about the atmosphere right now, especially above the surface? They're all based on observations at surface and aloft and so on, but especially the depiction of the atmosphere aloft is very important for how the model is going to get started. And if everything went right, and really good information gets collected and ended up getting put as input into the model, it can work really well, but so many things can go wrong. The truth of the matter is we have no way of really getting a perfect depiction of what the atmosphere is doing right now. There can be problems with the equipment, there can be calibration problems, equipment can fail, maybe, we only launch those weather balloons at a finite number of places around the Earth and practically nowhere over the ocean. Maybe we didn't depict the atmosphere, maybe what the initial conditions we gave the model weren't perfect. And so there's one garbage in, garbage out. If you didn't tell the model what the right conditions are now, there's no way the model can make an accurate forecast of what's going to happen 24 hours from now, 36 hours from now, 72 hours from now, or whatever. This is what was horribly referred to as the butterfly effect, and I don't want to get bogged down in the butterfly effect. I hate that term. Man, Ed Lorenz, the guy who kind of figured this whole business out of chaos and so on, he must really regret this analogy they made about the butterflies and butterfly effect and how it came really from this diagram called the strange attractor, which kind of looks a little bit like a butterfly. But this idea that there was like small imperfections in how the business of climate initial conditions were being described blew the forecast. Well, he must hate that, okay? But it does tell us the truth. If we don't have perfect initial conditions, the model simulation will go wrong. It's just a matter of when it'll go wrong. And since, the basic idea here is sound. If a weather prediction we have a problem that really cannot be easily overcome, we know the physics of the atmosphere really well, but you have to have basically perfect initial conditions to feed to the model as input if you're going to have a forecast that's worth something. And that's unobtainable. There is no way to get sufficiently perfect initial conditions. So for numerical weather prediction, the weather in the first couple of days is a problem with obtaining initial conditions that are effectively perfect. But the initial conditions are not the only kind of input that goes into a model. There's also a type of input called the boundary conditions. And again, this was described in more detail in the 100 level stuff. But the boundary conditions are the external processes that are driving the atmosphere that are not related to like things we observe from day to day using routine weather observations. They're things like the solar output. Okay? The amount of energy arriving at Earth's orbit from the sun varies from time to time, and it has nothing to do with measurements of temperature in Omaha, right? How should I put it? Measurements of temperature in Omaha aren't causing the solar output changes. Changes in the solar output can be changing the temperature in Omaha. Changes in the chemical composition of the Earth's atmosphere, like the addition of greenhouse gases and so on. The overall albedo of the surface of the Earth and so on. These kind of factors are external to the 7 primitive equations. They're inputs. We have to tell the model what to assume for the albedo at the surface of the Earth at this grid point. We have to tell the model how much the energy the sun is emitting at any given time. We have to tell it that. That's input into the model, but it's not what's called an initial condition. It's called a boundary condition. Okay, this is a term that comes to us from mathematics. Both numerical weather prediction models and climate models have to have these boundary conditions as input to them, but it turns out these boundary conditions don't actually make a huge impact on day-to-day weather in a numerical weather prediction model. If I ran the numerical weather prediction model for 24 hours into the future to make a forecast, and then I ran the model again with exactly the same input except I changed the amount of carbon dioxide in the atmosphere, it wouldn't really change the forecast at all. Because even if I doubled the amount of carbon dioxide, it would take longer than 3 days to increase the temperature of the Earth. Okay, we would still get basically the same forecast. Numerical weather prediction needs these information of these boundary conditions, but it's not really very sensitive to them. But these factors, these boundary conditions, have a huge impact on climate timescales. Over the course of years and decades, these are the factors that determine what the climate of the Earth is going to be. If I double the amount of carbon dioxide in my climate, I run 2 simulations. One is with the observed amount of carbon dioxide in the atmosphere, and the other is with double that much. If I iterate both that control run and that experiment run 3 days out into the future, we can't see the difference. If I iterate them 30 years out into the future, the one with double carbon dioxide will be radically different than the one that had observed amounts of carbon dioxide in the atmosphere. See how these 2 kinds of factors, those initial conditions and the boundary conditions, don't work the same way. The initial conditions are a deal breaker for numerical weather prediction, and they're basically unobtainably, you have to have basically perfect information. And we live in a real world. We don't have perfect information. It's just a question of how good our information is. Meanwhile, for the boundary conditions, they don't really make that big of an effect on numerical weather prediction, but they're the whole story when it comes to climate. Scientists understand these processes really well. These these boundary condition problems, like these solar output, the chemical contribution in the atmosphere, the albedo of the Earth, we understand those things really well. And changing these things are what we do in climate simulation. We're going to be making changes when we run a climate model. We're going to have a control run with observed conditions, and then a experiment run where we increase the amount of methane in the atmosphere, or we change the solar output, or we increase the amount of carbon dioxide in the atmosphere, or whatever. And the 2 models, the experiment and the control, will be different. And it turns out that the effects of how different, in terms of they'll be different in the sense of what the global mean temperature is in the control run versus the experiment run. And those differences turn out to not be crazy sensitive to the changes in the boundary conditions. It's a good thing, too. Let's say I run an experiment. I have a control run with observed values of carbon dioxide in it, and I have an experiment run where I've taken the amount of carbon dioxide and multiplied it by 2. So I have a twice carbon dioxide run. That's my experiment. And I see, look, the double carbon dioxide run has a higher global mean temperature. Good science. All right? But it's not terribly sensitive to the fact that it's double carbon dioxide. If I change it to 2.1 times the amount of carbon dioxide, I'm not going to get a radically different answer. I'm not going to suddenly find out, but if I made the amount of carbon dioxide 2.1 times as great, suddenly I get a colder Earth. Or I get an Earth that's 5 times warmer than when I doubled it, or something like that, doubled the carbon dioxide. No, it's going to give you the same answer, maybe a little bit warmer. Okay? It turns out the effects of these boundary conditions are important, but they're not terribly sensitive. Okay? We can make a assumption that the amount of carbon dioxide doubles. Okay, will the amount of carbon dioxide in the Earth's atmosphere double? It's going to change. Is it exactly going to be double? No, I mean, it's going to be either more or less than that. But more importantly, it does not, from the point of view of climate simulation, it doesn't really matter. As long as we have broadly gotten these things right, the climate simulation is going to be fine. I didn't invent all this stuff. Climate science didn't invent all this stuff. This business of initial condition problems versus boundary condition problems is a thing that comes to us from theoretical mathematics. It comes to us from the kind of people who do research on the business of differential equations. It's the kind of thing math PhDs pore over. These terminology and an understanding of the fact that there's a difference between an initial condition problem and a boundary condition problem is something that's well understood from theory point of view and so on. Numerical weather prediction turns out to be an initial condition problem. Climate modeling turns out to be a boundary condition problem. And math gives us ways to understand and put error bars on them and so on. Both initial condition problems and boundary conditions are a mess. Both of them are well established in terms of like mathematical theory and so on, and they can both be really trouble with regard to like numerical modeling. That's how busy math PhDs spend their days, is figuring these kind of things out. But in the case of climate modeling, it turns out that our ability to model the climate as a boundary condition problem is pretty good. Okay? Mathematicians can analyze the equations that we're using in terms of boundary condition problems, and in fact, our understanding of that is pretty good. It isn't necessary for us to have unobtainably great observations of the boundary conditions in order to have a good climate simulation. I don't have to know that the amount of carbon dioxide in the atmosphere is going to hit 600 parts per million versus 610 parts per million versus 590. That's not important. Okay? Turns out whether I run the climate model with 590 parts per million or 600 parts per million or 610 parts per million carbon dioxide, I get basically the same answer. Okay? So that's great. Science loves those kinds of problems that are not terribly sensitive. If I got radically different answers with tiny different amounts of carbon dioxide in the atmosphere, we'd have a mess. But we don't. We get basically the same answer. That's good. That's a good boundary condition problem. Makes climate scientists happy. And it turns out the initial conditions don't particularly matter. In a climate sense, remember, initial conditions were the deal breaker for numerical weather prediction of 72-hour forecasts or something like that. But it turns out, if I give my model, let's say I do 2 simulations. One, I run the model for 100 years, giving it as initial conditions January 1st, 2000. And then I have another run where I give it a different set of initial conditions. January 1st, 2001. Okay, I gave them their different initial conditions. And when I run the model out, the 2 models are going to be very different in terms of their day-to-day weather. But the 2 models will in fact have basically the same climate. Both of those models will have, even though they have different initial conditions, if I run them with the same boundary conditions, the global mean temperature in the 2 runs will be basically the same. The boundary conditions are what's determining the climate, not the initial conditions. That's great. That's really good news. But see, here's the deal. It kind of sheds a light on the fact that another problem with this argument that Skeptic was having. Not only are weather and climate 2 very different kinds of problems, but they are asking for different kinds of answers. When we are looking for numerical weather prediction answers, what we want is, what is the weather going to be like 3 days from now? That is a very interesting question. But you're not asking, what is the global mean temperature 3 days from now? You're asking things like, at a specific location, at a specific time, what's the weather going to be and how is that different from the weather someplace close? That is a very important kind of question. But that's a numerical weather prediction question, and that's the kind of question that, frankly, meteorologists get wrong a lot. We can do it. Numerical weather prediction works for some finite period out into the future before eventually problems with the initial conditions catch up with us. But, for a forecast of maybe even as much as 4 or 5 days, maybe a little more, maybe a little bit less, we can make forecasts of what the weather is going to be, where we can actually see how the weather in Omaha will be different from the weather in Des Moines, or how the weather in one location, or what time the front will come through and bring precipitation at this location versus that location. Fine. But that doesn't work like hundreds of years into the future. It works like a few days into the future. Then the initial conditions have caught up with us. But here's the deal. I don't give a rat's ass. Nobody gives a rat. I can't believe I just used that expression. I don't care what the weather's going to be doing 100 years from now. I don't care what 100 years from today the weather is. That's not the answer I'm looking for when I run the climate model. What I'm looking for is what the global mean temperature is. And actually, I don't even really mean like what the global mean temperature is 100 years from today. I mean like what is the global mean temperature in the 2010s. I'm sorry, the 2110s. Or the 2120s or whatever. Okay, for like a period of 10 years, 100 years from now in the future, what's the global mean temperature? That's the kind of questions I'm answering. The answers, or if we start picking this apart in more detail, things like how much wider is the tropical belt 100 years from now than it is from now, or whatever. And honestly, even things like the exact temperature of the Earth 100 years from now, it's not that terribly interesting. Frankly, as long as I know, like, oh, I see, in the model it's getting warmer at this rate. That's probably enough. The trends are probably as much science as I need, okay? Oh, that's very, very different. I mean, if we go back to our straw man skeptic, the skeptic wasn't entirely wrong. We can't forecast the weather 100 years from now, but that's not the point. Climate scientists do not care about the weather. They care about the climate. They really don't. The skeptic who said we don't know what the weather's going to be like 100 years from now is right. That's not the issue. We care about what the climate's going to be 100 years from now. And not one day in that 100-year run is right. Every single day will look very different than what the real world will be doing on January 1st, 2050. Okay, or January 1st, 2060, or whatever. But that's not the point. The point is the climate that simulated weather is in will be fine. That's really interesting. That's really important. All right, now, as we get started here, what I want to do is I want to ask a couple questions before we move forward with the new material. I appreciate your patience with this rather long kind of review of the things you saw. Question 1. Numerical wet models of the atmosphere produce forecasts based on the 7 primitive equations, which are A, a set of differential equations that describe the physics of how the atmosphere works, B, actually 7 physical models of the atmosphere, C, which are solved based on past observations of the atmosphere and the climate system, or D, equally applicable in any branch of science, such as chemistry or astrophysics. Okay. This question might take you more time than you think. Take a look closely at those 4 options and get a little feedback before you move on to question 2.